Hi, this is James Woods. We're firing up our poster session for how much does household behavior count. Uh, I am not the only one in the room. Right now we also have over here.
Lauren Heiser.
And
Mitra Moisey.
thanks. So let's go ahead and work through some of the slides. And what's in front of you should look quite a bit like the poster that's behind you. And we'll on occasion refer to it as well as to quite frequently each other. So we're going to be focusing on how much household behavior actually counts within building energy simulations, and mostly we're going to be focusing on what you see when you're dealing with Energy Plus. And we'll focus just on Energy Plus, even though that we know that there are many alternatives to that one, but that's going to be our main simulation engine. So let's talk a little bit about variability. And you guys jump in whenever you feel like doing this, because we're a little bit on the live side. I'd like to present you with Hairstyles of the Beatles. I thought this was an interesting motif because it shows that there's a great deal of variability within the populations and also over time. But it also highlights one of the problems that you can have dealing with building energy simulations, and that's dealing with averages. And we're focusing here on the Beatles in 1967, which was, I think, the Sgt. Pepper album. The baby boomers around me will have to verify that this is correct.
I remember that. I remember that. That
Remember
sounds
it?
right. Yep.
And
Sgt. Pepper.
what I'm pointing out here is that there's significant differences between, say, John and Ringo. They look different, they sound different. John has absolutely no sense of rhythm. Ringo actually does. Ringo can't sing. John can. And if you took the average Beatle, I'm pretty sure that you would not end up with basically the average song on the album coming out, which I have decided which is Strawberry Fields Forever. There are songs which are better than that and they're worse than that on the album, but that's the average one. But what you'd end up with is, you know, the average Beatle would have John's sense of rhythm and Ringo's singing voice. And so you have to be fearful of using averages, pumping them into a music-making function and coming out with something else. Also, want to point out that there have been significant variations in behavior over time. I mean, just look at, you know, John's facial hair over here. In 1970 is Let It Be. This is when everything was really starting to freak out. But there are differences in behavior over time, and you should expect to see change. Even though the averages are still there, a person itself doesn't necessarily have an average on a day, a week, a year. There are always going to be variations as they adapt to changing circumstances, like the breakup of the Beatles. So we're going to do a quick exploration on what you can learn about averages, and we're going to find out a little bit about what happens when you make those kinds of assumptions. There's certain wrong things that can happen to you, and we're going to look at consequences of having those wrong things happen. Mostly what we're going to be doing is playing with the consequences of something that's called the triangle inequality, which says that you should be very fearful of reversing where you take an expectation when you're trying to find the average of a function of some random variables. And we'll talk a little bit about how it's possible to get out of this problem by doing lots and lots and lots of simulations in order to get to real probability distributions. So let's take a bit of a history, and here's where I'll pass things over to either Lauren or Mitra. By the way, we'll go ahead and do Paul McCartney hairstyles for the years that the papers were published. And what we have there is the picture I have of Paul McCartney with a mullet, and I knew once I saw that picture it had to be in there.
It had to be there. Yeah, McCartney with mullet. Well, in '78, Paul was wearing his mullet, and Sokolow and Sonderegger were studying energy use in identical townhouses in Twin River Study, which is a classic in the field, and looking at the effects of people who moved in and out of these dwellings, and in fact discovered or estimated that about half of the variability was due to occupant factors. The Twin River studies that followed in '78 suggested that neighboring townhouses, identical in structure, could vary in consumption by a factor of 2. Next slide here. Hackett and Lutzenheiser, you're truly looking at identical apartments in Northern California had similar kinds of findings, and in fact, in subsequent research, discovered that with you taking air conditioning into account, you'd actually find a case where there were vast differences between households that were demographically identical as well as in identical structures. And then the work by Pedersen in 1994. Which I'm not aware of.
I tested simulations and found that occupants could accounted for more variation in climate and heating and cooling. If you didn't know the occupant behavior, your heating and cooling was off by 25 to 40%, which limited the final accuracy of any sort of estimation.
So there's a long tradition of discovering considerable variation across the household population in multifamily and single-family units, and the real problem has been to try to sort out the behavioral effects from the technology and building effects. At the same time, common practice in modeling for design and audits is to hold behavior constant or assume an average kind of consumer occupant in building.
And we're going to be taking off from that in that we're going to be holding the building constant, the weather constant. The only thing that we're going to be moving around is the behavior. And so we're trying to do in simulation what was done in the 1978 papers that were there, as well as the 91 papers. Just changing the behavior a little bit and see what those consequences are, holding everything else constant. And, well, what do we care? Why is it going to matter for us? And the two problems that we have are in simulation going to be bias and precision, the variability that's there. And I think the one that people have focused most, almost completely on, is the degree of precision. The idea that you can do a building energy simulation and you're lucky to get within 20% on that from what's true. Not having precision on an individual building with specific people in there has certain consequences for what you can do. One of the things that's happened is that there's been this focus within the tools on refining the physics models, making sure that the airflows are right, having the ability to model a window with varying gases inside the two planes, making it so you can put screens on the windows, making it so you can put in a certain amount of dirt just to make sure that you get the airflow just right, and focusing on these little incremental improvements, the kind of things that can refine accuracy by 1% or 0.25%, something along those lines. And what we're saying is that if behavioral is such a big chunk, perhaps the effort that goes into getting that 0.25% improvement in precision that you have in the physics models can get you something like a 10% improvement on the behavioral side of things. And so that would be a better use of time and effort and research funding. The other thing that can happen if you're focusing on this precision attribute is that if you're doing simulations that are focused on certain behavior, that you know that the person is always going to open up the windows at the right time, that you know that the thermostat settings are always going to be this, is your technology tends to be focused on that assumed behavior. And so if people are going to act always in this way, you can get a lot of energy efficiency by tuning things quite precisely to that kind of behavior. And the example I have is that, you know, if you know that everyone is going to turn on their air conditioner once the temperature reaches 82 degrees, it has a different implication for sizing of air conditioners than if you're, you know, uncertain whether the person's going to have it on 2 hours a year or something along those lines. And so what we're looking at is being able to have technology that works over a wide range of behaviors rather than one specific behavior.
Yeah, and on the other hand, there are studies that show if you try to develop buildings that are resistant to occupant behavior, that can lead to significant oversizing and other sorts of inefficiency and efficient design.
So there's a sense in which, too, I guess we're saying that you know, seemingly innocent decisions to use estimates of sort of average behavior or normal behavior of some sort to the modeler or the designer may actually end up specifying certain kinds of equipment that fit that particular behavior pattern, where if in the real world behavior is much more variable or quite different from that, even the technology itself would have been incorrectly selected.
Now, we also are going to have bias that comes into play here, and this is going to be things that you happen because you're sticking in average behavior and saying that what you're going to come out with is going to be average results, which isn't always true. And when you do have this bias in play in the simulations, it means that your forecasts are also going to be biased because your average behavior does not give average results. This is kind of a common statistical flaw that's there. The example I usually give is that if you want to find the average on a die roll, you know that you can just add them up and divide by 6 and you end up with 3.5. But if you do something like you want to find the average of your die roll squared, you can't just take 3.5 and square it. It doesn't work. You get the wrong answer. And by putting in that kind of certain behavior, even though it is on average correct, doesn't necessarily give you the correct result. And that will bias again your forecast in the future. But it can also result in, as we've said earlier, inefficient specs. So if you look at something like the ACM model for Title 24, it gives you some thermostat settings, which may in fact be on average correct, but it doesn't necessarily give you the average results in a building energy simulation. Of course, the other thing that may happen is that you have this bias here, but you don't always know it's going to be the same. So if you're depending upon these building energy simulations, and you're just looking at moving this one thing, and depending upon the bias being the same, you can't be exactly sure of that at all.